Hello there, Mr. Sutton bringing you this introduction to circles. In this one, we're going to identify different parts of a circle and use properties of tangents to find segment lengths. For the real-life application here, we're going to find the range of a GPS satellite. Let's start with the most basic term. What is a circle? I mean, this is a circle right here. We can draw a circle, but what does it actually mean to be a circle? A circle is the set of all the points that are equidistant, in other words, the same distance, from a center point. And we name circles using their center. So we can call this one circle C, and we can actually write out the word circle or use this little symbol here. Let's talk about some of these segments that we've created within the circle now. The radius of a circle is a segment whose endpoints are the center and any point on the circle. So a radius goes halfway across the circle because it's from the center to the outside. So for example, radius AC. There's also radius BC and CE, and note that I'm using the little segment symbol here to note that this is a segment. Now, another kind of segment in a circle is a chord. This is a segment whose endpoints are both on the circle. So for example, chord DF here. And then finally, the last kind of segment in a circle is called a diameter. This is a chord, but it's a special kind of chord. It's a chord that contains the center. So the diameter goes all the way across the circle. So for example, diameter BE. And note that the diameter, since it goes from the outside of the circle to the center and then back again, is going to be twice the radius. At this point, we're now going to talk about some lines that intersect circles. A tangent line is a line that intersects a circle at exactly one point. So for example, tangent line RX right here. And note that I put the little line with arrows on it to show that it is a line and not just a line segment. Now, a point of tangency is a point where a tangent intersects a circle. So a point of tangency, one point here would be this point X. And a common tangent, that's a line that is tangent to two or more circles. So for example, this line right here. And the last kind of line we'll go over here, this line that's intersecting the circle in two places, is called a secant. Intersects the circle at 2 points. So secant WY, and note that again that I'm using a line notation here instead of just a segment. If I just wrote WY with no arrows on this line up here, then it would be a chord and not a full secant. Now you might wonder why we care about all these different terms. It turns out that secant lines and tangent lines are going to be extremely useful in calculus later on. So that was a whole lot of words and definitions. At this point, pause the video and see if you can give an example of each of those different things we went over based on this diagram over here. All right, let's see how you made out. So for the center, there's really only one option here, and that would be the point K. For the radius, we have a few options. One of them is this segment KD. You also could have used KJ or KG. And then for a chord, a few options here. The only one that is just a chord would be segment BF right here. Again, a chord touches the circle. It's a segment that connects the circle at two different points. However, this GJ is also going to count as a chord. But it's something a little bit more than just a chord, because JG or GJ, that's actually also a diameter. It is a chord that goes through the center, but it also counts as a regular chord. For a secant line, we need a line that goes through the circle in 2 points. The only line that does that is line AC up here. For a tangent line, we need to touch the circle in just one spot. One possibility for that is line EH down here. And for a point of tangency, that's a point where a tangent line is touching the circle. So that's point E right here. We're going to talk a little bit more about tangents at this point. There are two properties of tangents that we're going to find helpful. One of them is that tangents are always perpendicular to a radius in circles. So if you have a tangent line intersecting a radius, we always know that this is going to form two right angles. Next, tangent segments from a common external point, like in this picture here, we have this common external point and two tangent segments coming out from it. these segments are always going to be congruent. We're going to do some problems involving tangent lines now. In the diagram below, PT is a radius. They're telling us this is a radius of circle P. We want to know if segment ST right here is tangent to circle P. Now let's think back to those two tangent properties. Which one would help us here? Oh, how about the one about radiuses, radii, and tangent lines being perpendicular? If ST is truly a tangent line, that means that this angle right here, angle PTS, is going to be a right angle. Well, how could we figure out if this is a right angle given these three sides of this triangle? Oh yeah, use the Pythagorean theorem to test it out. So pause the video and go ahead and do that. All right, let's see what we came up with. So out of these three sides, 37 would be our hypotenuse, our C value, using the Pythagorean theorem. So we can say 12 squared plus 35 squared equals 37 squared, question mark? Because we don't really know yet. We have to test it out. Plug in those in the calculator. Let's see what 12 squared plus 35 squared comes out to. 1369. And how about 37 squared? That comes out also to 1369. So since this passes the Pythagorean theorem, that means that this is a right angle, which means that yes, ST is indeed a tangent line. In this next problem, we are given that T is a point of tangency. Based on that, we want to find the value of the radius, r, of this circle. Pause the video and give this one a shot. So in order to figure out r, we need to set up a relationship that relates all of these different sides of the triangle. Since we have a right triangle, and we would know this, by the way, even if they didn't put this here, because this is a tangent line meeting a radius, since we have a right triangle, we can use the Pythagorean theorem here, but be careful when you're setting this up. So we have r squared for one of our sides plus 80 squared equals, now this 50 here is just the part that's outside the circle. To get this entire hypotenuse, we need r plus 50, and then we need to square that. So squaring all this stuff out, 80 squared is going to be 6,400. Over here now, don't forget to either use the shortcut or write this out twice and FOIL it. Either way, we're going to get r squared plus 100r plus 2,500. These r squareds can cancel out. That's kind of nice. Subtracting 2,500 here, that's going to give me 3,900. And then dividing by 100, we're going to get r equals 39. In example 4, we're given that rs is tangent to the circle at S, and RT is tangent to the circle at T. So we've got two tangent lines from a common external point. Based on this, pause the video and see if you can figure out the value of x. So the key fact here is that these two tangent lengths are going to be equal, because we were told already that if you have two tangents from a common external point to the same circle, they're going to be congruent. So we just have to set these two things equal and solve. Subtracting 4, we've got 24. Dividing by 3, we get x equals 8. To wrap this up, we're going to do a real-life problem that incorporates all of the wonderful tangent theorems we've just talked about. So GPS satellites they orbit about 11,000 miles above Earth. Mean radius of Earth is about 3959 miles. Because GPS signals can't travel through Earth, a satellite can transmit signals only as far as points A and C, as shown in the diagram. We want to find the length of BA and BC to the nearest mile, so we can figure out how far this GPS can transmit signals. So pause the video and see how far you can get on this one. All right, let's see how you did. So first key fact here is that since BA and BC are both tangent lines coming from a common external point, they're going to be the same. Whatever BA is, BC is, and vice versa. So we just really have to find one of these, and that'll count for both of them. Next, it sure would be nice if we had a triangle somewhere in here. If we draw a line from E to C, that is just going to be another radius of the Earth. So this EC is just going to be 3,959 miles, just like ED. So we can set up the Pythagorean theorem now and figure out a missing side. We just have to be careful here about where our right angle is. because the radius meets the tangent line at a right angle, this is our right angle here, ECB. So when we set up our Pythagorean theorem, we need to do EC squared, so 3,959 squared, plus whatever BC is squared, equals this whole side from E to B squared. So that's going to be 3,959 plus 11,000 squared. And now I'm just going to do pretty much this entire thing on the calculator because I'm out of room. So let me get my calculator out. So I've got 3,959 plus 11,000 comes out to 14,959. I'm now going to square what I just got, and that gives me this right half of the equation here. From that, I'm going to subtract 3,959 squared. So here we go, 3,959 squared getting subtracted. Gives me this insanely large number. And now I am just going to take the square root of that answer. I'll do second minus here to just put the answer in there. So that comes out to roughly 14,425, actually 26. And that's going to be in miles. So this concludes our first out-of-this-world lesson on circles. Until next time, this is Mr. Sutton, signing off.